Hi, everybody. Welcome back to the L'Hopital's rule practice set number 3, part 2. In this part, we still continue working on the form is infinity over infinities here. And just try to refresh your memory. Those are the 10 problems we will try to practice on. And from the part 1, we finished 5 of them. So for here, we're going to start problem number G here, all right? So as always, if you did not get a chance to practice the remaining problems, right now it's a good time to pause your video and go ahead and try to get the problem done by yourself first, and then, resume the video and come back and check answers here. Okay, so now go ahead if you want, pause your video, and I'm going to switch to the whiteboard and talk to you in a few minutes. Hi, I'm back, and I'm back in the whiteboard here. So let's try to continue to practice our L'Hopital's rules with the form infinity over infinities, right? So, okay, so here, the part G's here is the x approach to A. To the right-hand side, that's why I put a plus. And then this is the natural log EX minus EA. And then the top here, this is a cosine X, and this is a natural log X minus A. So like always, we check first, right? So the X is approach to the A plus. So this is a natural log approach to the 0 from the right-hand side. So I know this one's here going to what? Approach to what? Negative infinities, right? And then this one's here, the EX is here. So this one also going to approach to the 0 from the right-hand side. So what happened here? This one also going to approach to the negative infinity. So we have infinity over infinity. So we can use the L'Hopital's rule and try to find the limit. Okay, so in here, let's see here. So now this is a limit x approach to A plus, from the right-hand side. So the cosine here, because I know this one going to approach to the cosine A's, right? And the cosine is always bounded by, like 1 and negative 1. So we really can take the cosine out here. And then in here, I can have the limit x approach to A. And then I have a natural log EX minus EA, and then the natural log X minus A here, right? So the reason why I want to move this one out here is because I don't want to use like a product rule, those things will make the problem so kind of complicated here, right? So I know this one's here going to approach to the cosine A, so it's a constant here. So now I can use the L'Hopital's rule for this ones here, right? So I can apply the L'Hopital's rule for this ones here. Okay, so now let's see what we have here. So this one's here is a cosine A, then limit x approach to A from the right-hand side. Then I take the derivative. So natural log derivative is x minus A over 1, because the chain rule is still 1. So the natural log EX minus EA, so it will be EX minus EA. And don't forget what? The chain rule here, right? So EX minus EA, the chain rule will be what? Will be EX, right? Because EA is a constant here. Okay, so now I have here, so let's see here. So I have, this is the cosine A, right? And then this is the limit x approach to A to the right-hand side. And then in here, instead of simplify, I can change this as 1 over EX, correct? And then in here, I can flip this one, it's x to the A to the right-hand side. So this is x minus A to the EX minus EA here, right? Okay, so now this one said the reason why I want to change this one out is because this one's here, it will give me what? 1 over EAs, right? So it's a constant here. So now I have two constants. Now I just need to, so this one's here, if you let the x approach to the infinity, so this is still will be, oh, so this one, sorry here, this one turns out, okay, so because the x approach to the infinity, oh yeah, so this one will be infinity over infinity. So I can use the L'Hopital's rule only to the remaining part to make the calculation a little bit easier. So the first two terms, I have e to the a and cosine a, correct? Okay, so now I can take the limit x approach to a from the right-hand side. Then the L'Hopital's rule on the bottom, this is x minus a, so x is 1, right? Then here the top derivative is ex, because ea is a constant here. Now, okay, so here this is a cosine a, ea. So what happened when the x approach to the a to the ex here? We have what? We have ea's here, right? So boom, boom, these two cancel. So what do we have here? It's a cosine a's here. Okay, so this one's here is a little bit tedious, but I think to show, tell us some good skills here. That means if you have some constant, the easy one, you can, take it out, and then that will make your L'Hopital's rule is a little bit easier. Okay, so you don't need to use like a product rule, those things. Okay, let's take a look at problem H here. This is u, okay, so this is u approach to the infinity, then u cube, then this is e u to the 10th here. Okay, so now the same way we always check. So this will go to the infinity. So e to the infinity will go to infinity. So this will go to the infinity. So we know this is infinity over infinity. So now I can use the L'Hopital's rule. So eu to the 10, you take the derivative. Exponential function is itself eu. And then don't forget what here we need to do, chain rules, right? So this is 1 over 10. So those are very good review about your derivative. So then the bottom here, this is 3u to the square. So if you take a look again, so what happens here? Well, so here, this will be, so what happens here? So this will be infinity over infinity again, right? Okay, so now let's do, we say, okay, if infinity over infinity, we can use the L'Hopital's rule again. So we'll simplify it. I move those constants out, right? So I don't need to worry about that. So it's 1 over 30. So this is the limit u approach to infinity. Then you take the derivative u to the square. So what is here? 2u's, right? Then the eu to the 10 still by itself. Then the chain rule again, right? Okay, so now I combine a little bit to the constants, right? So I move these constants out, so simplify it. So what is here? 2 times 3 is 60, so this is 600, right? Then limit u approach to infinity. So this is u to the 10. So I plug the u into the infinity, so this is infinity over infinities here, right? So what do we do here? One more times, right? So we do one more time. So this is 1 over 600. So this is the limit u approach to infinity. So u take the derivative is 1. Exponential is u over 10, and the chain rule again. Wow, so this is 1 over the 6,000 limit u approach to the infinity, e to the u to the 10. So what happens when the u go into the infinity here is e to the infinity. So the whole thing is equal to what? Infinities here. All right, so this is so this limit is going to the infinity. So as you see, how many times we need to do the L'Hopital's rule? I think 3 times, right? Okay, so now let's do the next one, the problem I here. So the problem I, so this is a limit x approach to infinity, and this is x cubed, and then this is e to the negative x squares here. Okay, so for this ones here, as we always did here, let's try to change this one. So limit x approach to infinity. So this is x cubed, e to the what? X squares, right? Now you put the infinity here, this one will be the infinity. This is infinity, right? So e to the infinity is infinity. So I know this is infinity over infinity. So what do we need to do? L'Hopital's rules, right? L'Hopital's rule, so it's a limit x approach to infinity, x cubed, 3x squared, exponential, ex squared, chain rules, 2x, right? Okay, so now let's simplify a little bit. So this is 1x, I can cancel 1. So I can move the 3/2 to the front. So limit x approach to infinity. So now I have x e to the x squared. So still checking infinity over infinities, right? Okay, so let's do the L'Hopital's rule one more time. So this is 3/2. This is limit x approach to infinity. This is 1. This is x squared, chain rule, right? So it's 2x here. So what do we have here? So when you have the infinity, x to the infinity, the whole thing here is going to what? Infinity. So it's 1 over infinity is what? It's 0. So the constants in front doesn't matter. So the whole thing, this one approach to infinity. Cool? Okay, now let's take a look at k here. So k, this is the limit x approach to infinity. So this is ek, and this is xn here. And this problem will tell you a very important rule, so we're going to mention till the end. Okay, so the first things you see here, this is infinity, this is infinity, right? Because infinity to the nth power is infinity. So if you take a look at the L'Hopital's rule, so what happens here? So this is limit x approach to infinity. The derivative here is ex. Then the derivative on the bottom is x to the n minus 1. So you check again. So it's still is infinity over what? Still is infinity over infinity. So let's take a look at one more, and then maybe you can see the patterns here. So then here, this is x approach to infinity. So this is ex again, right? Then this is n, then n minus 1 to the xn minus 2. So you put here, this still is infinity over infinity. So as you know, you need to use the L'Hopital's rule many, many times, right? So what is your L'Hopital's rule till the end? Because after you take all the nth power, so this will be the ex, and this is what? N to the factorials, right? Okay, now you let the x approach to infinity. So this will be e to the infinity. So what is here? So this is infinities here. So this limit approach to infinity. So basically, the problem K tell you one very important thing. That means if you have exponentials here, right? You have exponential and you have a polynomial. So exponential approximately to the infinity is way faster than the polynomial. So that's why when you put them together here, right? So that's why you're going to the infinities here. Okay, now let's take a look at the K part. Oh, I'm sorry. Oh, this should be the L part, right? So let's here, the last problem. This is a limit and the x approach to the infinity. And here is the natural log x and x to the p here. And they give a very specific, they said the p here has to be greater than 0, right? Okay, So now we see here, this is the, you know, when you try to do that, this is the infinity over infinity when x equal to the infinities, right? So now let's try to do the L'Hopital's rules, right? So if you do L'Hopital's rule, natural log will give you 1 over x. Then the xp, so this will be the p, x to the p minus 1s, right? Okay, so now, like we did before, you can combine this x to the denominator, right? So what do you have here? So this is 1 over p, then the x, right? So this is xp minus 1 times x, so it will be xp's here. So that's why in here, this condition is quite important. It's p greater than 0. P greater than 0, that means this number going to stay on the denominator, right? So this is p greater than 0 here. So that's why when the x approach to infinities, right? So this approach to infinity. So the p is positive, so stayed in the denominator. So what happened here, the whole thing in the denominator approach to 0. So this will be equal to what? Zeros here, right? So that's why the limit here, and in here, be careful when the p has to be greater than 0 here. That means the polynomial. So this one also tell you, that means the natural log and the polynomials, right? So the natural log, you know, the polynomial go faster than the natural log. So that's why when the x approach to infinity, the natural logs here will go slower than the polynomial. So that's why the denominator approach to the infinity faster. So that's why the whole thing's approach to zeros here. Okay, so that's it. That's the practice set number 3 here. And this is the part 2. We finished the remaining 5 problems here. And so remember, practicing. That's the way, that's the key factor to make you get good at math here. Okay, so nice to work with you guys for this practice set, and looking forward, let's go to the next practice set. We're going to talk about the one, how about if you have 0 times infinity? So what type of the things we need to do to find the limits? Okay, so nice to talk to you and have a good day. Bye.